Right, so in this video we're trying to introduce the idea of a double integral over a rectangle, okay? First things first is the notation, right? In Calculus 1, we use the integral notation, definite integral from a to b of some function f of x dx. That was the notation. It might have been shortened to just say the function f over an integral I, over an interval I, where, let me finish my dx here, the integral of f dx, where I is the interval a to b. Okay. So this notation extends to calculus 3, that we might want to have an integral, but it'll have to be a double integral because the function f has two variables, okay? And we're going to be integrating over r for region, okay, instead of I for interval. And then we're going to have to put dA, and dA is meant to be either dy dx or dx dy. We'll need to talk about that notation and the differences between them. So this is the notation, and in section 15.1, we're particularly wanting to focus on regions where the region is a rectangle. Okay. So the picture of this problem is going to look something like this. We have a function given, z is equal to f of xy. That function will be given, and we know that it will look like some sort of surface in three-dimensional space, x, y, z. Okay. We're then specifically going to be given a region down here that is a rectangle. So here's our region R being a rectangle. And that rectangle may go from x going from A to B. And then on the y-axis, we might be going from a value of y going from C to D. So here is our rectangle, and it can be described as x by y, and we would say it would be the interval A to B by the interval C to D. Okay, so the notation for the double integral would look something like this. Whatever function you want to evaluate the definite integral of, and then we could either, because it's a rectangle, dA could either be dy dx, in which case y would have to go from C up to y is equal to D, and then x, the second integral, would go from x is equal to A to x is equal to B. And that's just the notation, okay? Or you might have had a double integral. Whatever function you're trying to find the double integral of, you could have done dx dy, in which case x would have gone from A up to x is equal to B, and y would have gone from C up to D. So these are the two notations for the definite integral of a function of two variables. So this is a double integral. Okay. In the next picture, in the next couple slides, we need to talk about, like, what is the meaning of this? Like, what is the meaning of this notation? Okay, what does it mean in context? And then how do you actually evaluate this notation? How do you actually evaluate this to a number? Is it a number? Right? What is the meaning of that number? Okay. So I think we can see by analogy from Calculus 1 that what we're trying to do is this integral, right, from Calculus 3, we know that we can look at each of these edges and draw their images up onto the surface. And it will turn out, by the way we're going to define this double integral, that we're going to be computing the equivalent of area, which in this case is volume. So this double integral is going to end up computing a volume. Okay, and here is how that happens. Okay, we have in this picture Okay, a function has been given to you. Okay, so I'm giving you the function that f of xy is equal to x plus y. And it looks like we've been given the rectangle. X is going from 0 to 4 and y is going from 0 to 8. So here is our x-axis, here is our y-axis, and we know that the plot of x plus y is just this plane. Okay, now I've got two of these pictures drawn. Okay, so I would like to show what we can do, how we would do the Riemann sum to try to figure out what this definite double integral is going to be. Now with a 1D Riemann sum, you have to split the x value up into different parts. But here in Calc 3 we have x's and y's, so we need to split the x and the y into parts. And so we want to split the x into one rectangle, and we're going to split the y into also one rectangle. So it means we're going to take 0 to 4, we're going to have delta x is going to be b minus a divided by n, so delta x is equal to 4. And then the m value is how many times you want to split 0 to 8 up into pieces, and that will give you delta y, which is going to be 8 minus 0 over 1, which is equal to 8. Okay. So basically what we've done is we've split this rectangle up into only one piece, right? And then we'd want to choose to figure out where to evaluate the function on that one rectangle, right? And I like to choose the upper right corner, right? So what we're going to have is that we're going to evaluate the function at that one point, and that would give us this rectangle that would have a volume. So the volume of that pink rectangle would be the area of the base, which we got from delta x delta x times delta y, multiplied by the height of the box. So we would have gotten 8 multiplied by 4, which would have been the area of the base, and then the height of the rectangle would have been the function evaluated at x is equal to 4 and y is equal to 8. Okay, so this gives us the z value. So this box right there would be a volume of 32 multiplied by 12. And that would be the volume of that box. Now you can see that that volume is too big, so we have kind of over approximated. Okay, so here's what we'd like to do is we would like to maybe try to make more rectangles. Okay, so what if we had n was equal to 2? You would split the x-axis into two rectangles, so you would have from 0 to 2 and 2 to 4. Okay, so we would have that. And then let's say that you also try to use m is equal to 2, which is to split the y-axis up into two rectangles. So from 0 to 4 and from 4 to 8. And now what you can see down here in the, we've got here, and then we had a rectangle this way. So now I hope that you're seeing 4 rectangles forming right here, right here, right here, and right here. And now we need to choose to evaluate the function at certain points of those rectangles. And again, I always like to do the upper right corner. Okay. So if we try to compute, then we're going to get a rectangle here. And that's going to stick up a little bit. You evaluate the function at that right corner, it's going to come up to the surface here. This box may be a little bit bigger. Evaluate the function at that right corner, you're going to have a box here, and then evaluate the function at this corner up, and we have these four boxes. Okay, and we would like to add up the volumes of those boxes now. Okay, and the way to do that would be to come over here and do the math. We would have the function evaluated at 2, 4 plus the function evaluated at 4, 4. That's this point and this point. And then you'd want to add that to the function evaluated at 2, 8, this back corner, and then add that to the function at 4, 8. Okay. And then you would want to multiply that all by the area of the base. Since we divided them equally, we're going to have the area of each of those bases is a 2 by 4 block. So that'd be 2 times 4. Okay. So that's what we would need to do, and I'll just have the computer do those numbers. Oops, sorry. Got a little confusing, sorry about that. So we have our function defined, f of x is x plus y. I'm gonna do the function evaluated at 2, 4, plus the function evaluated at 4, 4, plus the function evaluated at 2, 8, and then add that to the function evaluated at 4, 8. Okay. Now that's the height of all those individual rectangles, but they all have the same area, which was the area of the base was 2 multiplied by 4. Okay. And so the computer should be able to add all that up to get 288. Okay. Now, we know that that's only an approximation. Okay, that's only an approximation. So we would need to add more rectangles to get a better approximation. Okay, and that's what we can do, what we'll show how to do in the next video. Okay, but just to show what we're going to be shooting for, you can add a page below, right? Essentially that we have got the definite integral of x plus y dy dx. Y was going from 0 to 8, and x was going from 0 to 4. Okay, that's the definite integral, and we've shown that with n equal 2 and m equal 2, that we've shown that you get an approximate answer of 288. Okay, the exact answer, okay, can build on something that we already know from the fundamental theorem of calculus from Calc 1, that basically what you want to do is just see this double integral as two integrals separately. Okay, so the first thing we want to do is to focus on the y integral, in which case you need to find the antiderivative, but you need to find the antiderivative with respect to x. So can you imagine what function you need to take the partial derivative of with respect to y to get x plus y? So for example, if you look at x multiplied by y plus y squared over 2, right? If you take the partial derivative with respect to y of that, then we have x plus y. And that is what makes this an antiderivative with respect to y. So there's our antiderivative with respect to y, and then you can plug in the limits 0 to 8, just like you would with the fundamental theorem of calculus. So you would get 8x plus 64 over 2. And then you plug in y equals 0 on the bottom limit, and you get 0. So for the first integral, we get 8x plus 32. And that is what then goes to the next integral, the x going from 0 to x is equal to 4, 8x plus 32. And you can see here that calculus 3, a double integral becomes just two calculus 1 integrals in a sense. And now we're down to a calc 1 integral, and you can integrate with the Funwell theorem of calculus 8x squared over 2 plus 32x, evaluated from 0 to 4. So that will give 8 times 16 over 2 plus 32 times 4 minus 0. So what is that? 64 plus 32 times 4, whatever that number comes out to be. Okay, it's a big number, kind of like 288 was a big number. So what we're going to see in the next video is what happens as the limit as n goes to infinity and the limit as m goes to infinity. What happens is we take more rectangles in both directions. And we will hopefully get the same number that we got here. And that's the subject of the next video.